Okay, so you might be thinking, why am I looking at bread? Well, we're looking at bread because of what we're going to talk about today. And what we're going to talk about today is finding the volume of something that has a flat bottom and a top that changes height. So if I wanted to find the volume of a loaf of bread, what I could do is, instead of finding the volume of the loaf, find the volume of an individual slice and then multiply that by how many slices I have. Or if I couldn't do that, find a volume formula for a slice, and then as the loaf changes, I could change my volume formula. So if I look at all these loaves of bread, I've got like this flat bottom right here, and then the loaf that kind of makes a square. So one could describe this loaf of bread as having a flat bottom and rectangular cross sections, because if I look at this loaf of bread, it's kind of a square or a rectangle face with, it's got a little bit of depth to it. So I really get a whole bunch of like rectangular prisms that I'm adding together. So I want you to kind of keep that image in your mind as we talk about this next part. So if we go to the actual notes here, what we're really doing today is the volume of cross-sectional solids. So what we can do is, to find the volume of a solid, we can find the volume by integrating a of x dx. Now, why is it a of x dx? Well, because if I have a cross-sectional solid, and again, say like I have a loaf of bread here, let me see if I can draw a piece of bread. I'm so talented. Wow, that actually isn't so bad. So if I kind of draw my piece of bread here, all right, it's not just a flat piece. It's like it's a solid. It's a rectangular cross section. And if I wanted the volume of this piece of bread, I would do the area of the base times the height. So the area of this times that. So in our case, we could call that a of x for the area of the bread itself times dx, where dx is that little change in depth there. Okay, so if I want the volume of a piece of bread, I could take the area of the face times the depth. If I wanted the volume of a loaf of bread, I would add all of those together, which in calculus, when I have an infinitesimal add, I use this integral symbol. Okay. So if I want to find the volume of something by what we call slicing, I can sketch the solid in a typical cross-section, find a formula for the area of a face, find the limits of integration, and integrate to find the volume. So let's actually get to this here. Find the volume of a solid whose base is the region enclosed between y equals x and y equals x squared, and whose cross-sections taken perpendicular to the x-axis are squares. Okay, what does that mean? Well, it means I'm going to take y equals x, which is this guy, and I'm going to take y equals x squared, which is this guy, and I'm going to use this as the base of a loaf of bread. Okay, so pretend for a second this is the base of a loaf of bread. And then what we're going to do is we're going to fill this pan. Okay, so let's say this is the bottom of a bread pan. I'm going to fill this pan with magic yeast. Yes, I heard that. You heard that right. Magic yeast. So Mrs. Vibber is going to sprinkle some magic yeast in here. And what's going to happen is I'm going to have bread grow in that pan, so that to figure out how tall it grows, the yeast rises in a way by saying, first, the yeast uses a magical tape measure and measures this distance right here. And however wide this is how tall the bread grows, and I get a piece of bread right there. And then it measures this distance, and however tall that is, it grows another piece of bread. Measures this distance, grows another piece of bread. And imagine that these blue boxes are coming up out of the screen to get you. And I have all these slices which end up looking like this. So in this diagram, here's y equals x. Here's y equals x squared. And then these pieces of bread from the magic yeast measured this distance and then grew up, over, and down to make a square. Okay, so magical yeast, the volume of a solid whose base is the region enclosed by y equals x and y equals x squared, cross sections or squares, would look like this. Okay, imagine kind of a loaf of bread. Well, if I want the volume of that loaf, we never taught you a volume formula for magic yeast bread when you were in geometry. That's what calculus is for. So if I want to find the volume of the bread, I would take one individual piece of bread, that looks like this, and I would try to find a volume formula for it. Well, that individual piece of bread is the same as this guy right here, and it comes from a representative rectangle. So I'm going to just resketch this so I can draw my rectangle a little bit more clearly. So I take a representative rectangle, except instead of using it now to find area, I'm going to use it to find volume, because this representative rectangle is now in 3D, and it makes this box. Where the rectangle itself is down here, making this dx, and the height of the rectangle is now here, and this height came from top minus bottom. And if this is a square cross-section, that means this is also x minus x squared, making the volume of this box length times width times height. And if I wanted to add all the boxes together, I would do this for every square all along the line. Okay? In calculus, though, we're going to do an infinitesimal addition because our dx is going to be infinitely small, so I have infinitely many pieces of bread. So if I want to find the total volume, I'm going to take the integral of x minus x squared squared dx, and I'm going to do that on the region on which I'm shading. Y equals x and y equals x squared intersect at the origin, and they also intersect at 1. So I'm going to take the integral from 0 to 1. So this is now the integral from 0 to 1 of x minus x squared squared. I'm going to pull up my calculator, do that in said calculator, math 9, 0 to 1, x minus x squared squared dx. And the volume of this teeny tiny loaf of bread is going to be 0.03 repeating. Mrs. Vibber, is that 3 decimal places? Yes, it is, because the bar means I actually wrote an infinite number of 3s. You just can't see them. So that's the volume. Now, I want to kind of backtrack for just a second and say, did I actually follow the rules up here? The rule said to find your volume, you do the integral of a of x dx. Did I do that? Well, the integral of a of x dx means find an area formula for your cross-section. Well, my cross-section is a square. The generic area of a square is base times height, where base and height are the same, so the area of a square is really just side squared. Well, I found the length of a side to be the difference between the two equations, and I squared it. Side squared became x minus x squared squared. So yes, I followed the rule. All right, let's move on to the next one. Find the volume of a solid whose base is the region S, so I'm talking about this part, and whose cross-sections taken perpendicular to the x-axis are semicircles, okay? So this says I'm going to take this, I'm going to pretend it's the base of a magic yeast loaf pan, I'm going to sprinkle my magic yeast inside, and then from this, the magic yeast is going to measure these distances here and grow semicircles. Like this. Okay, fine. So if it grows semicircles like that, that means each of those rectangles becomes the base of a semicircle. You got to be impressed with my artistic ability here. So I have this thickened semicircle. So this little distance dx is now my depth, and this distance right here is the distance between the two curves. So it's top, which is 2 minus x cubed, minus bottom, which is tan x. And the volume of a cross-sectional solid, a magic yeast solid, the volume of a cross-sectional solid is supposed to be the integral of a of x dx, where a is the area formula for the cross-sectional shape. Well, the area of a semicircle is pi r squared over 2. Because a circle is pi r squared, so a semicircle would be half that, dx. So now I need to get r in terms of x. So my volume is going to be pi over 2 r squared dx. All right, so this thing right here is the distance across the bottom, which means my radius is half that. So r is 2 minus x cubed minus tan x all over 2 squared dx. And now I need to know my limits of integration, so I definitely go from x equals 0 up to where these guys intersect. So let's figure out where that is. So let's see. Tan x, and the other one was 2 minus x cubed. I'm going to try and zoom 6 this and see if I can see it in a normal viewing window. That looks pretty good. My baloney has a first name, it's Oscar. My baloney has a second name, it's Mayer. Because Oscar Mayer has a way with Bologna. Okay, so what am I looking at here? I'm looking at this little region right here, and I want to know where they cross. So I'm going to do second calc intersect, first curve, second curve, and because they do intersect more than once, I'm going to move my guess close to the intersection I need. 0.9021555. Okay, so this thing right here is A, and A is 0.902155. And I'm going to quickly store that as A. Ta-da! Fantastic. Okay, so 0.902155. So I want to integrate from 0 to A. Nice little side note here. You can do this whenever you want. You can use letters as long as you identify what number that letter represents. So over here, I identified A, and now I'm using A. Everybody's happy with that. You can write it down and put an A there, or you could put 0.902 there. Nobody cares. So I'm going to go back here and actually integrate now. So I'm going to math 9 from 0 to A of pi over 2 times, all right, I'm going to write this as a fraction, so alpha y equals, and 2 minus x cubed minus tan x, and that's all over 2. And then I'm supposed to close this parenthesis and square it and put a dx there. Do my integrals look alike? I think I did it correctly. I'm going to hit enter and get 0.69433. And there's my volume. But you got to admit, there was a lot of parentheses and, fractions and stuff like that. There is a quicker way to do this. So when you have semicircles, and every time you have semicircles, your radius is always half the height of the rectangle. So you're always going to have a difference that's being divided by 2. So what I can do with this is say, wait a minute, that's the integral from 0 to A of pi over 2 times 2 minus x cubed minus tan x squared over 2 squared, right? I can distribute this squared to the top and the bottom. This guy can combine with that guy to make the integral from 0 to A of pi over 8, 2 minus x cubed minus tan x squared dx. So when you are doing semicircles, which you will be doing often, there is a nice shortcut. Instead of doing pi over 2r squared, just remember that that turns into pi over 8 times the difference squared, because then you don't have to worry about the parenthesis as much. Oakley dokley. Okay, and then you might be thinking, Mr. Why would I have something that's perpendicular to the x-axis that looks like semicircles? Like, what is the point of this? Well, let me tell you what the point of this is. The point of this is bananas. So I'm going to come back over here. I am going to delete this, if I can figure out how to do backspace on here. I don't even know how to do backspace on my own computer. There it is. Half banana sliced. Okay, so here's a banana, and I have a sliced banana. Well, this isn't really what I wanted. What I was looking for is this guy right here. If you slice a banana lengthwise, okay, and then I were to flip that over and slice these in cross sections, wouldn't I get a flat bottom and semicircular slices? Yes, you would. You're right, I would. I make bananas for my kids all the time, and I put milk and a little bit of sprinkles on them. You put sprinkles on anything, my kids will eat it. And there you go. You got what you need. This is exactly what we're talking about here. Okay? It's a half a banana that I sliced up to find the volume. Okay? So, where was I? I was back over here. That's what we're doing here. All right. Come on, OneNote. There we go. Let's do two more here, and I'll do these a little bit faster. So the volume of a solid whose base is the region R and whose cross-section is taken perpendicular to the y-axis are rectangles whose height is twice their width. So now I'm slicing this way, and I'm going to use that, and I'm going to grow rectangles, big, tall rectangles whose height is twice their width. So if I draw my rectangle here, it looks like this. And this distance right here is that distance, which is an itty-bitty distance along the y-axis. So that's dy. And then this is going to be in terms of y. So I have y equals 2 minus x cubed, which means x cubed is 2 minus y. So x is the cube root of 2 minus y. And up here, this would be x equals inverse tan y. And so when I find the difference, I want to go right minus left. So the right-hand side is going to be the cube root of 2 minus y, and the left-hand side is inverse tan y. So there's my width, and the height is twice the width. So this height is 2 times the cube root minus inverse tan. So the volume of a magic yeast cross-sectional solid is the integral of a of x dx, which in this time we're going to do dy instead. So my volume is the integral of the area of this rectangle, which would be base times height. So 2 times the cube root of 2 minus y minus inverse tan y squared. That would be this times that would equal this. So the integral of a of x dx, but dy in our case. And now I need my limits of integration shading in terms of y. So I go from y equals 0 up to the y value of this intersection. Here's a neat trick. The y value of this intersection still comes from that point A that we found before. I'm going to come back over here, and I'm going to do vars y-vars function y1 of A to get the y coordinate of the intersection. Does that make sense, everybody? Think about that for a second. I have the x coordinate. I would just plug it into the function to get the y coordinate, so I did that right here, and I'm going to store that as B. 1.2657 B equals 1.2657. So I'm going to integrate from 0 to B. So I'm going to come back to my calculator. Math 9, 0 to B of 2 times the cube root. You know what? I don't want to find the cube root button. Go away a second. I don't know why it does that. All right, so 2 times 2 minus y to the 1/3, because that's a cube root, right? Minus inverse tan y squared dy. Remember, your calculator doesn't need to say y. It just, here's variable, and that's what it uses. 1.175. So volume equals 1.175, and there is the volume of that. Okay, seriously, last one. I don't know how long this has been, but I'm sure it's long enough for you. So find the volume of a solid whose base is the region enclosed by sine x and that other thing whose cross-section is taken perpendicular. Okay, equilateral triangles. So the integral of a of x dx, a of x needs to be, let's see, x-axis, so I'm in terms of x. Equilateral triangles. So let's think about an equilateral triangle. All these things would be the same, and those angles are 60 degrees. You know what I'm going to do for the area of an equilateral triangle? Instead of doing 1/2 base times height, I'm going to use that area formula that you learned in Algebra 2. The area of a triangle is 1/2 AB sine C. So this is going to be the integral of 1/2 a b. Well, since a and b are the same, it's going to be something squared. Sine c, well, all these are 60, and the sine of 60 is root 3 over 2. Does that make sense? 1/2 a of x dx is going to be 1/2 ab, or a and b are the same, sine c dx. All right, so let's sketch this bad boy. So I've got the square root, not the square root, the tan x, and then I have x squared minus pi x, and that guy looks like this. And so I'm dealing with this region, and I'm going to take this and grow some equilateral triangles out of it. So let's see, my base of my equilateral triangle goes from sine x down to x squared minus pi x. So this is going to be sine x minus x squared minus pi x in parentheses. Pardon the tiny text there. And let's see, I need to know where they cross. Well, they would cross at 0 and pi, of course. And there you go. So I'm going to put that in the calculator. Math 9, 0, pi, 0.5. And then I have sine x minus x squared minus pi x squared times root, nope, that's a pi, root 3 divided by 2 dx. Da, 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 da. 8.56129. But Mrs. Fibber, that's more than 3 decimal places. I don't care. You just need at least 3. And then I am done. Oh no, but I forgot a joke. I forgot to look up a joke this time. Thinking, what joke can I use? Landon just had a good one the other day that he told me, and now I can't think of it. I don't know. What did the cat say when it hurt its foot? Meouch. I know, it's terrible. Somebody bring me a good joke. I gotta find other ones. I'll ask my Alexa at home for a joke. All right, I'm done now. Have a great day. Bye.